Thank you, Keiji. Thanks to organizers to organize this very nice workshop in this challenging environment. And I will speak about some exact results on dynamics of quantum circuits. Maybe this does not directly relate to main theme of the workshop, which is hydrodynamics, but it might be maybe eventually also useful to some hydrodynamics ideas. So anyway, so this is about general frame of dynamics of interacting systems and about chaotic dynamics in particular, so non-integrable dynamics. And this work is somehow, I mean, at least my talk is somehow divided maybe in three kind of sections, three type of results, which I'm going to discuss. First is spectral statistics. Second is dynamics of correlation functions, which might be particularly interesting for let's say hydrodynamics and transport. The last is about structural stability. So, and maybe, you know, I think I'll be quite comfortable with time, but still, in case I'm gonna need to speed up at the end, maybe I just stress right away that the results which I will discuss might seem at first sight very, very fine-tuned. Well, I mean, not more fine-tuned than the results on integrable systems. Definitely, integrable systems are more fine-tuned, but anyway, these are still fine-tuned systems. And contrary to integrable systems, which we all understand are very fragile, they are sensitive to perturbations. I will claim that lots of aspects of this type of dynamics is structurally stable. So, I mean, most of this claim is based on conjectures, but we have at least one but simple result, which is kind of almost rigorous in a sense, which was basically the theme of the last PRX that I mentioned in my slide. So this is a joint work with two heroes here, Bruno Bertini, who was a postdoc in our group until last year, and Pavel Kos, who just finished PhD basically on this theme of my talk. So again, I mean, just to explain why I put a caricature of CatMap here, I mean, for those who have some background and interest in classical chaos and classical dynamics, like me, this is a kind of challenging, perspective is to kind of find exactly solvable models of quantum chaos or quantum many-body chaos rather, which would be analogous or parallel to this exactly solvable models of classical chaos, which you find in textbook on dynamical systems like CatMap. So the idea is to find, I mean, you know, we all expect that chaotic systems are something very complicated, and it will be very hard to get exact solutions. But this is true, of course, for generic non-integrable chaotic systems, but there might be systems which are much simpler, which allow for exact solutions because of their special features like linear automorphisms on tori, or so-called cat maps, or Baker maps, for example, in classical dynamical systems theory. So, I mean, yeah, if you want, the motivation is to find such models in quantum many-body dynamics. And just to start with some simple kind of structure, which we will introduce, based on which everything will be based, that I will talk about. I mean, the backbone structure, which I'm going to use, is this dual unitarity. So, I mean, you imagine that you have quantum dynamics, which is based on the property of unitarity. It means that, you know, and also, I mean, you would like to have something which you can, you know, scale in the sense that you can define an extended system. So, and the perfect framework for scaling system is a quantum circuit. So you take a linear array of qubits and you just couple pairwise, right? As I will show you later. But now, before we go into any kind of many-body, let's just start with this simple two-body gate, which you can consider as a scattering operator, where you feed in two states, I and J, and you get as output two states, which you call K and L, right? I mean, this is, and I assume that these states belong to finite dimensional Hilbert space, like d-dimensional Hilbert space. And since, you know, I want the evolution to be quantum, I want this gate to be unitary, right? For lots of things that I will talk about, you can also imagine that this gate is stochastic. And then, you know, you could build, let's say, Markov circuits out of stochastic gates. So for people who have interest in more statistical, classical statistical or stochastic dynamics, maybe one can make a kind of a parallel story with respect to what I'm going to say, and still you can find exactly solvable cases of stochastic systems, for example, in a very parallel analogous way. But for the purpose of my talk, let's assume this is now unitary. And what I'm going to use now or define is that this becomes unitary also when you reshuffle the gates, so that is when you take I and k as in gates and j and l as out gates, or vice versa. I mean, unitaries are reversible, so if you just transpose, it's also good. So the idea is to define what we denote as this U tilde, which is the reshuffled gate, and which means you just replace gate k and j. You just kind of reflect across the diagonal. And in this way, you define this U tilde. And now what we will ask is now that this dual gate, which is acting in the space direction, now time direction for me is always vertical, space direction is horizontal. So, I mean, what we'll ask is that both of these gates are unitary. So basically dynamics defined in both perpendicular directions is unitary. I mean, I would now maybe want to make a disclaimer here. I mean, there has been discussions in the quantum information literature about tensors, which are so-called perfect tensors, which corresponds to unitary operations, no matter in what way you distribute your indices. So in this case, I have 4 indices, so I could distribute them in 3 groups of 2. But I will not require unitarity of the third kind of third partition, because this partition is not related to spatial or temporal evolution. It's not related to a simple evolution in extended system. So I mean, what I want to say is that this is a weaker constraint as a constraint for a perfect tensor. I mean, perfect tensors are more exceptional and more, they don't exist in certain dimensions. These things I will show later exist in any dimensions, in particular for qubits, and even more so for higher dimensions. Okay, so now what I'm going to do with these gates is I'm going to contract them. So for example, when I use unitarity, I will just contract vertically. So for example, I will take red and blue gates. Sometimes with red, I will denote the gate itself, and with the blue, the Hermitian adjoint gate, so the inverse gate. And when I just vertically contract the gate with itself, with its Hermitian adjoint, which is inverse, I can just, then it means this is identity, which means I just take two free I get just two free lines, two straight lines, which symbolize the identity. And similarly, since these gates are dual unitary, I can also contract them sideways. And when I do sideways contraction, I get this two kind of sideways identity, if you want. I mean, this is just a diagrammatic description of these two formulas. Yeah? And this is something that, my talk will be, I hope, very non-technical, as non-technical as it can be based on the subject, but still, probably it's nice to appreciate that there are some simple, this is, one can do almost all the algebra using just plotting diagrams, essentially. Okay, so now, for example, now let's go from single gates to a quantum circuit. So now let's define these Bricor quantum circuits, which people in quantum computation like very much. There are many ways in which you can define this type of, first of all, this dynamics is discrete in time. It's like a FLUCTUATIONS. So let's assume that these gates are all the same. They may be the same, maybe not, but if they are all the same, this is like a FLUCTUATIONS, which is translation invariant in space, translation invariant in time, if you want. And these gates, again, I draw them in this way as I did before, that these wires have 45-degree angles. So you can read this evolution or this way or that way. So, so for example, this is an example of a gate of size L equals 6, which means I have 6. This is 1, 2, 3, 4, 5, 6 gates, and then you displace them by one side. These are, if you just do like this, this is just what I call as even time step and odd time step, even time step, odd time step, and each time step is just a tensor product of these 2 qubit gates. But then I take a shift for the odd layer, right, so that I get this mutual, kind of interaction, which then couples all the qubits together. Okay, so now the point is, the main point I want to make here now is that I can read this picture vertically or horizontally. It looks the same. So it defines, and since this gate is unitary in both ways, it defines a unitary many-body system in both directions. So we can define a dual quantum circuit propagator, this W tilde, which is defined in a very similar way, but now it's defined on a circuit I mean, suppose we have periodic boundaries, not to make things too complicated. So now these periodic boundaries can be think sort of as in time or as in space. So if you do it in time, then this corresponds to evolution of a chain of qubits of size 2t rather than 2l, which you then have to propagate for L time steps. So basically what you have now is this duality of traces, which means you can write a trace of the propagator to power t as a trace of the dual propagator to power L. So then, I mean, of course, in the language of statistical mechanics, this is just two ways in which you write a partition function of two-dimensional statistical model in terms of row or column transfer matrix. But now this is not statistical mechanics, this is quantum dynamics. So these propagators are unitary. And what I ask now, based on the features of the models I just defined, that both of these transfer matrices are unitary propagators. And yeah, this has been actually, since I will not go back to our first paper on this, which is PRL in 2018, I'll just mention it. And that this concept of dual unitarity basically generalizes this concept that we introduced in 2018, which is a self-dual, or yeah, we call that self-dual Kiff-Teasing model. So there is a particular line in parameter space of an Ising chain coupled with non-transverse, non-longitudinal, so tilted fields. But the particular values of the couplings, spin couplings, and the fields, this corresponds to dual unitary circuit, which was actually shown by in this paper by Krishnan and Lamakraft. And then this concept of dual unitarity, actually well, not dual unitarity, but space-time duality, in Kiff-Teasing model was actually first discussed by a group of Tomaz 2016, and also even earlier by Boris Gutkin in classical models. I mean, he noticed that even some classical multi-particle cat maps can be understood as having this space-time reversal symmetry. Okay, but you know what we kind of probably noticed for the first time was that one can actually use this to compute something interesting. For example, like a spectral form factor. And now I'll just outline in next two slides. I will just outline the essential of this. Not even going through any detail, but just what we can say about spectral correlations based on this feature of dual unitarity. So so I mean, yeah. So if you want, I mean, now take a many-body system and you want to characterize its whether it's chaotic, quantum chaotic or not. I mean, since this model has no Lyapunov exponents, I mean, the Hilbert space dimension is fixed. It's 2, for example, for qubits. So this means that you cannot really take any semi-classical limit, which means you cannot really define chaos based on chaoticity of a classical limit, as people usually did in quantum chaos. So one has to define it solely in terms of spectral statistics. That is, whether the spectral correlations are described by, let's say, random matrices. And the simplest spectral measure of spectral correlations is the two-point spectral function, or its Fourier transform, which is called spectral form factor. So we start from a spectral density, which is just take a spectrum of a, and in our case, of course, we work with the systems which are discrete in time. So we imagine that this is a Floquet system. So the fundamental building block of the dynamics is one period of time propagator, which is sometimes referred to as the Floquet propagator, which is this object. And then look at its spectrum. And you can imagine this spectrum now as this unitary operator. The spectrum is a gas in one dimension. I mean, it's a set of points on a unit circle. And you can imagine this set of points to be a gas in one dimension, and you want to understand correlation features of this gas. So for example, you want to compute its density, and from its density, you can compute a density-density correlation function or the spectral pair correlation function. And you're doing the Fourier transform of that, you find what people define as spectral form factor. So in spectral form factor is just another way of representing two-point correlation function now in Fourier space. But the Fourier space with respect to a circle is time, right? So now the argument becomes time. And actually you can write this spectral form factor as a trace of the propagator to power t modulo square. So you see, I mean, the point is that you have many body dynamics for which you can compute trace of u to the t. which is just a partition function of some statistical look-alike model. Now, if you can compute that in certain ways, then you can basically target computation of spectral form factor. Now, the problem is that, of course, you have to do a two-replica calculation because this is trace of e to the t modulo square. And since there are fluctuations, I mean, usually these things, I mean, this is the problem in this business, is that this object is not self-averaging. So it doesn't really make sense unless you define some sort of disorder or some sort of random parameter which you will average over. And then, of course, you have to compute this type of object, which means expectation value with respect to some distribution of parameters of k of t, which is trace of e to the t square. That means you have to do the two-replica calculation. But anyway, I mean, this can be done. Okay, so before I show you how this can be done, I just tell you how this looks for random matrices. For random matrices, you find a very particular, very characteristic features of spectral form factor. For example, for unitary matrices, this is just linear in T until the time which is given by the dimension of the Hilbert space, which I denote as curly M. And after that, it saturates. So this is sometimes referred to as the Heisenberg time. Now, for the orthogonal matrices, for matrices which correspond to systems with time reversal symmetry, so for orthogonal ensemble of matrices in Floquet systems, these are usually called circular orthogonal matrices. Then the spectral form factor starts with a slope which is twice t, 2t, and then again at times of the order of Heisenberg time, it approaches the separation. I will not discuss the symplectic ensemble because I do not need it at all. But then what I will say also is that the Poisson, so that is for systems which are integrable, one usually uses the so-called Berry-Tabor conjecture to speculate that, or to conjecture that the corresponding spectral correlations should be those of Poisson, uncorrelated points on an energy axis, which have Poisson statistics, which means if you do the form factor, this is just a constant at the plateau value. So see, I mean, if you want to distinguish chaotic, many-body quantum chaotic system from an integrable system, then there is this huge gap. So for a many-body system, at short times, these values are of the order of short time versus the Heisenberg time, which is exponentially larger. So unless there is another time scale, which usually exists, which is the so-called tau-less time, such that, you will only get agreement with random matrices for times larger than tau-less time. And then depends on how this tau-less time would scale. But if tau-less time doesn't scale very strongly with system size, and usually it does not, usually it scales like power law, like L squared, for example, through diffusive systems. So, I mean, imagine now you start from a time in which random matrices start to work, and you compare it to a value for integrable systems. This is usually in system size exponentially large gap, which means that this object is a very sensitive detector of chaos. Yeah. Okay. Now, let me just give you one slide description of what we can actually do with these dual unitary circuits. I will show you later more concrete ideas, calculational ideas. But I'll start with this just to show you, what one can do, and later describe something simpler. So, for example, and the reason why we can do that is, again, I mean, this is probably clear from this formula. I hope it can be clear. But before I try to explain this formula, let me just explain you the setup. So the setup now is to take a random circuit. Now I will take a Floquet circuit with, let's say, in principle, two distinct unitary gates, which are dual unitary. So these two gates are dual, both of these two gates are dual unitary. They have to be dual unitary, otherwise we can't do the calculation. And then you kind of decorate this with single qubit gates, which are different and different sides. So these are the gates which kind of parameterize disorder, if you want. I mean, this system is, you can think of this system as being a disordered system, but you can also think of this as a technical tool. In a sense, the results that I'm going to discuss or present actually is true also in the limit of zero disorder. The problem is, of course, that the zero disorder limit does not commute with thermodynamic limits, so you have to take thermodynamic limit first. So it's really, the statement is about the disordered system, but for arbitrary weak disorder. There is no transition. So the disorder transition is a disorder equal to zero. So, and this is how I designate things. So this is a fixed two qubit gate, and this is a disordered one single qubit gate, all different colors, different gates. But then, of course, also in second layer, I mean, there are two layers. time has two layers. There are 2 layers of gates, and after that everything is repeated because it's a flocking. And then what we can actually show, I mean, first of all, we can write a spectral form factor now as a usual thing. So it's a expectation value with respect to disorder, and this disorder actually can be, I mean, this single qubit use should be IID, so they should be uncorrelated. And that's fine. I mean, people usually consider uncorrelated disorder in this business, but they can also be distributed completely arbitrarily. So they don't have to be hard distributed. They can be distributed with some arbitrary measure in the SU2. The only problem, the only restriction is that this measure has to be smooth. It shouldn't be too singular. Okay, and then what we do is basically we write this thing, trace of u to the d square as trace over 2 replicas. So the product over 2 replicas, but then we can use dual unitarity, which means we use this formula, which we wrote this duality of traces. Oops, here. We use this duality of traces to rewrite this second equality sign. And we are here. But then we can, you see, I mean, now, since we are doing this now space-like, not time-like, space-wise, not time-wise, we can actually use the fact that disorder is IID, so that we can push the averaging inside the power. So now instead of computing the average of a trace to the power L, we can actually make a trace of this thing, which is now a transfer matrix in space direction of a two replica object to power L. So now the only thing now which remains is to control the spectrum, because we want to do thermodynamic limit. So we have to control the spectrum of this two replica transfer operator, disordered average. And this disordered averaging actually helps because it makes this object kind of well behaved. This object then is like an operator. It's like a quantum channel. In fact, this is like a vectorization representation of a quantum channel. So it has a spectrum which is within unit disk, on the unit circle, or inside unit disk. And what we should show at the end is that the only point at unit circle is at eigenvalue 1, and this point could be multiply degenerate, and the degeneracy of this point is actually precisely equal to the random matrix value of spectral form factor, which is T for generic unitary matrices. And that's the statement of the theorem which we can prove. So we can basically first encode the result of this calculation into computation of a commutant of a set of operators. So we identify a set of operators such that the value of the spectral form factor is just the dimension of the commutant, that is the number of linearly independent operators, which simultaneously commute with these operators. So these operators are just magnetizations in time direction and all possible interactions, spin interactions in time directions, which are all translation invariant. So what we need to show is that the only operators which simultaneously commute with those are translation operators. And there are T independent translation operators, right? All the possible powers of one unit translation. So there are T translation operators, and that's the value of spectral form.
Hi, Tomaz. Can I ask a very naive question? So this T here is still defined on integers, right?
Yeah, okay, yeah. So I mean, I mean, yes. I mean, that's of course the way we define the lattice. So we define the lattice such that the unit cell has size 1, and the integers have half integers denote the positions of the kind of the two staggered sublattices.
Okay.
So now, yes. So you see, this means that this also the time lattice has dimension T, but in fact has 2 T points, but it has T unit cells, right? So basically, the translation operator is defined for 1 unit, right? So two lattice constant is 1/2.
Okay. So I cannot, in the usual spectral form factors, I can think of continuous T, and here I should just be careful, right? I mean, if you're thinking about usual spectral form factor for some other chaotic Hamiltonians, this is not the issue, right?
Well, I mean, of course, that's particular for this type of models, the circuit models, which are discrete in time. Yeah, I mean, that's actually needed here because we want to swap space and time. So
okay.
I don't know how to do a continuous limits. I mean, these things are not. This usually does not work in continuous limit. I mean, because whenever you want to do continuous limit, you lose the unitarity.
Okay.
So yeah, this is really non-equilibrium. I mean, it's really kind of, you cannot do this for a Hamiltonian.
Okay, thank you.
Thanks. Okay, so now let's move on. I mean, if there is maybe other questions, because this is now end of my kind of section 1, and now I go to correlation functions. So, right. So now for these dual unitary circuits, actually it turns out, and this is much, actually, in principle, it's much simpler calculation. It's also much more intuitive. One can compute correlation functions exactly. And I mean dynamical correlation functions, which means I take two local operators and I place them somewhere in space-time. So which means I place them, for example, in this case, I take operators which I denote as A alpha. So these are all possible traceless operators for Hilbert space of dimension D. For example, for D equal 2, these are Pauli's, 3 Pauli's. For D equal 3, this is 8 Gelman matrices, and so on. So now I define D alpha beta is a kind of tensor of dynamical correlations, which means I place A alpha somewhere in space-time, and these sides, tau sides away, I place A beta. And these two have also spatial separation X. Now, since this is not exactly translation invariant, there is this staggering and 1/2. So I will just assume that these two positions are X and Y. Yeah, of course, everything depends on X minus Y. So place local operator at place X. One you also shift in time for t time steps. And now, depending on the initial on the position of the initial operator, I think this one I would call Y. Okay, on the position of this operator, then I define two correlators, which I will denote as C plus and C minus, and depends only on the parity of Y. On these parity issues or staggerings, this of course should be clear from the picture, but you know, maybe look a bit confusing in the problems. But anyways, now the only point I will use, because again, I don't want to spend too much time on this because it's not very deep. The only thing which I will use now is the fact that I have dual unitarity, which means that I have, you know, unitarity itself already means, because I have these local interactions, this is like quantum cellular automata, correlations can only propagate by one side in one step, right? I mean, even if you look at this, I mean, this circuit, right? Everything I do here can only propagate, I mean, it cannot propagate there, right? And it can only propagate in this light cone, right? And the same I can now do for the space direction, right? I mean, since this, I can change space and time because both are unitary. I can also say that correlations can only propagate in space in the causal cone, which opens in the space direction. And so correlations can only propagate in the intersection of two light cones, one in space, one in time, but the intersection of two light cones is just light rays. So which means that the only correlation, non-trivial correlations which can propagate between A alpha and A beta is along the light ray, which goes right or left, depending on the parity of this position, right? If this position is here, then the correlations can only propagate along this ray. If this position is here, the correlations can only propagate that way. So in the end of the day, I mean, now, of course, I could use these diagrams, which I plotted in my second slide, to prove you, and the proof is not very difficult, but it would take us maybe 10 minutes. But I could prove that actually this is the only thing there is no vanishing, right? I mean, and I already said in words, I mean, this is because of this double causality. But you know, formally, you can just prove it by plotting these diagrams. So everything that remains, that everything that is in principle non-zero is this type of correlators. But these correlators actually are just single qubit correlators corresponding to a quantum channel. Now imagine what is this? I mean, you can just apply it. I mean, you can just think of one diagram as a building unit. So you start from A and you dress it with these gates and you just trace over this one. And then you get this object. You do it again, you get this object. You do it again, you get this object, and so on. So this is just like iterating this quantum channel, which is written in this standard representation like this. So, I mean, you have to do two quantum channels, n plus and n minus, depending on the parity of the initial site. So if initial site is odd, then this defines n plus. If it's even, we do define n minus. Okay, so now, bottom line is now that you have a unitary many-body dynamics, but if the gates have this dual unitarity property, then basically all the non-vanishing correlators in this dual unitary dynamics actually can be computed by a single qubit quantum channel, by diagonalizing single qubit quantum channel, because now this being just an iteration of powers of m This means that it can be completely written, spelled out in terms of eigenvalue decomposition of this quantum channel. So you just have to look at the spectrum and eigenvectors of the quantum channel and can write any correlator in terms of the sum of exponentials. So this type of models have correlation functions which are all exponentially decaying. Well, I mean, there could be non-trivial Jordan structure, so there could be some powers in front of exponentials, but in principle, this is what it is. Right, and now this gamma minus gamma plus, lambda minus lambda plus with index gamma, these are the eigenvalues of m plus and m minus. This eigenvalue, this spectra always contain eigenvalue 1, but eigenvalue 1 corresponds to trivial eigenvector, which is the unit operator. I mean, by the way, these quantum channels are also unital, so they preserve unit operator, they have to, and that's the trivial eigenvalue. Now you can classify, according to the scheme which is used in dynamical systems theory, you can classify ergodic behaviors based on the non-trivial parts of the spectrum. Depending on whether all eigenvalues are 1, then this will be non-interacting dynamics. In this Flocky circuit context, it is represented by a swap gate. Then you could have non-ergodic dynamics, but still would be non-integrable. I mean, yeah, you can have non-integral but non-ergodic dynamics as soon as one non-trivial eigenvalue is equal to 1. Then this corresponds to a conserved charge, conserved local charge, because this local operator will not decay. Then you can have ergodic and non-mixing dynamics if this eigenvalue, one non-trivial eigenvalue is on the unit circle but not at 1. Then you will get this. You will get some non-stationary charge. You will get a charge which is not converging, but it is oscillating indefinitely. So it's a kind of time crystal, if you want. And then in generic case, with the probability 1 in some random gate context, this will be all these all the eigenvalues, all non-trivial eigenvalues will be within unit disk, and then you get what you might call ergodic and mixing behavior. But again, along the slide codes. I mean, otherwise, the correlation function is 0. Okay, and then you may ask now. I mean, yeah, but how special it is, right? And I can just try to comfort you that this is not so special as you might think. That one can completely classify dual unitary circuits, dual unitary gates for qubits, for example. You take a general parameterization of for two qubit gates. So how am I doing with time, by the way, just to know that?
You have another 20 minutes, 20 minutes for talk.
For talk and then discussion. Okay.
Yes, yes.
Okay, so now, so now what you can do is you can provide complete classification for qubits, and you start from something that is giving you a completely general SU2 or SU4, sorry, 2-qubit transformation. It's written in terms of Heisenberg gate, which is V of J. Now, I mean, this would be general if one could put arbitrary Copley constants here. This would then be completely general, and then these are four actually general SU2, so single qubit gates, 2 by 2 unitary matrices, special unitary matrices, and then there is a phase. So this is 3, 3, 3, 3, 3, and 4, and 1 free parameters. This is 16 free parameters. And now, if you require dual unitarity, the only thing you have to fix is 2 out of 3 coupling parameters in the Heisenberg gate. So 2 out of these 3 J's have to be equal to pi over 4. So it means like it's a codimension 2 manifold in the manifold of 4 by 4 unitaries. That's the manifold of dual unitaries. So, I mean, of course, you can count independent parameters. It's less than 14 because of the symmetry, but still it's of the order of 9, I think, 3 parameters. Okay, so now examples. Swap is one example, of course, which is trivial. There are integrable gates which are dual unitary. For example, there is a particular trotterized XXZ chain where you take a Heisenberg gate without any decoration of 1 qubit unitaries. And then, of course, as was already pointed out in the paper by Lammacraft and Krishnan, one can write also Selfdual Kick-teasing model as a quantum gate, as a Selfdual quantum gate. One way to write this in terms of canonical parameterization is this one. Okay, and then there was another paper by a group of Tomaz who has also pointed out some generalization. So I mean, there were two papers where people discussed generalization of these dual unitary gates. For example, Claes and Lamacraft has proposed this type of parameterization for higher Hilbert space dimensions. This, of course, does not provide full classification for higher Hilbert space dimensions, but it provides a rich family of dual unitary gates in higher Hilbert space dimensions. And then, as I mentioned, Gutkin and company have kind of generalized Keck-Teasing model to higher local space dimensions. So there are kind of sparse results of people trying to go to higher Hilbert space dimensions, but there is no complete classification. And my kind of guess is that it's probably not an easy mathematical problem. Okay, so now maybe I will just skip this since I want to discuss a little bit about perturbative stability. I just want to mention that in the last year there has been many papers discussing these dual unitary circuits in various contexts. Also, in the context where circuits are actually not dual unitary, but still one can apply space-time duality transformation if you want, space-time flip, in order to get something interesting. For example, papers by Vedika Kemani and her group were trying to suggest that these entanglement transitions become very interesting for, if you can think of this measurement based on entanglement transitions in these measurement circuits, you could consider now the version in which the space direction of the circuits is unitary, right? This still would correspond to a valid measurement-based circuit. And now you can discuss, what happens when this space dynamics undergoes many body localization transition, provided one assumes that there exists. Then this might be related to this entanglement transition in the measurement-based circuits. Okay, so then one can, I just want to flash through one or two more slides before I discuss maybe last 5-10 minutes perturbative stability. So one can compute a couple of other interesting objects, which maybe are interesting from the point of view of complexity and characterization of complexity, let's say in quantum circuits. Probably the most attractive object is the operator entanglement. That is the characterizing complexity of growing operators or operator spreadings. For example, there was a calculation which we have done in our group for dual unitary circuits, which suggests that there is something interesting going on. So the idea is to try to set up a calculation for RNE2 entropy of operator circuit for operator spreading. So you take an initial operator, which is this A, and then you spread it, which means you propagate it in Heisenberg picture, but you look at it as a vector in space of operators, and then you do the 2 copies. So it's a 4-replica calculation. So 2 copies because you take operator rather than state, which means you use this so-called folding representation. So you treat operator as state, but now the gate becomes 16 by 16, not 4 by 4, because the wires become thicker. They encode Brian the cat of the state. So in this way, you get already 2 copies, but then you have to do also the 2 copies because you do the RNE2. So this is distinct. Then you do 2 copies of that, and then you do the trace. So you compute this. You compute this as a reduced density matrix, but then reduced density supermatrix if you want. But then you do the square of that and the trace. So it's 4 copies of objects like this. So in fact, if you want, it's basically 8 copies of the original propagator. So it's pretty tedious calculation, but and you have to do some assumptions. It's not fully kind of assumption free, but provided you do this sort of reasonable assumptions, you can come up with the curve for growth of entanglement entropy, which is discontinuous. And this J is this parameter in the classification, which is basically the main parameter. If you have J is equal to pi over 4, you get a swap gate. But J is 0, you get the maximally chaotic, let's say, Keck-Teasing, Selfdual Keck-Teasing gate. So it turns out that if this J is the key parameter, if J goes from 0 to pi over 4, Then first, there is a critical value of J in which, until which this entanglement grows with a maximal rate, and then it starts to decay. And at pi over 4, it decays to 0 because then you get a non-interacting gate. So this is analytical. I mean, the full curve is the analytical calculation, and then we compare it with some numerics. Then maybe before I go to the last part, I just want to maybe advertise a recent paper where I pointed out that maybe one can just make an analogous discussion for a kind of a different part, which one can call IRF circuits. I mean, there is this alternative way of writing 2D statistical models as interactional interface rather than vertex models. And of course, you can write any vertex models as IRF model or vice versa, but the price to pay is to increase the number of states, to square the number of states essentially. So for example, it might be advantageous for some cases to treat circuits which are generated by these control gates. So these are control gates, time goes vertical, where you apply SUD or SU2 transformation, provided, I mean, depending on the values of the qubits at the adjacent sites. So these are the so-called control bits, and this is the active bit. And you do this again in a staggered way. And one example of this kind of circuit is, for example, you might have heard this Rule 54 model, even though Rule 54 model is a totally classical model, but you can also interpret it as a quantum cellular automaton. And in fact, this model is exactly IRF circuit. But that's not chaotic, I mean, because it's integrable, has many features of integrable system. But this model, I mean, in general, taking this unitary transformations as arbitrary or general unitary rotations, this would correspond to a chaotic circuit. I mean, one can find that spectrum again is described by random matrix correlations and so on. So I'm just now giving one or two slides flash through what one can do. So starting with this control gate, three-qubit control gate circuit, you could just map it to an IRF model where instead of this, you would write a plaquette. And now this plaquette assigns a complex number to values of 4 indices around the edges. So it's exactly like you do in IRF models, but in IRF models, you assign a weight, which is a positive number. Now you assign a complex weight, such that this thing is a unitary transformation where these two guys are fixed. And then you can define, I mean, you can define correlation functions in these circuits, and you can compute correlation functions. And then you can define the dual unitary IRF circuits. You define folding, you define these diagrams, which are parallel of those diagrams I plotted in my second slide. So this would be unitary in time, this would be unitarity in space. And this would be like how you would define correlation functions graphically. And this for dual unitary IRF circuits, these correlation functions would be 0 unless these operators would lie exactly on this light rays, if you want. But now these light rays have thickness 2, not 1. And then the smallest, the thinnest non-trivial operators, which have non-trivial correlations, has support 2. So that has to do with the structure of IRF circuits versus this standard brick-wall circuits. I mean, I'm happy to discuss this in the discussion time. In this level, it's just kind of just to show that there is a different paradigm which has very similar physics. Now let me go to the last. So how much time do I have still, Keiji? 5 minutes, 7?
Yeah, 5 to 10 minutes.
Okay, thanks. So, so the last thing I want to discuss a little bit is, how to go to generic dynamics, how to make some perturbative expansions. And here I try to argue, as already said in the introduction, that these models might be structurally stable, unlike integrable systems. And there has been some, I mean, I would not say related results, because this is very different mathematics. But still, I mean, people who do dynamical systems in classical dynamical systems theory, they are, aware of this time. These results are actually very common, the structural stability results, namely that systems which are written as these hyperbolic flows, which are kind of everywhere unstable, are structurally stable. So if you shake a hyperbolic system a little bit, it still remains perfectly hyperbolic. So it is not like KAM, where you have an integrable system, you shake it, basically, almost all trajectories become chaotic. Yeah? So, of course, what I'm saying is this is completely different mathematical framework, so there is no reason why this should be true here, but maybe there is some philosophical reason, since this is far away from integrability. And I will try to show you that there is one simple set of results for which this structural stability indeed works. So let me just describe you in a few minutes what we did. So this was published like a few months ago in PRX. And so what we do now is, again, we write a general correlation function. Now what I will, notation that I will use here now is that the green gate is a generic gate, which I will write in the folded picture. So that is this is like U cross U transpose. So this is like you know, it's like this it's like this thing. I mean, instead of looking at the operator in the standard Heisenberg picture, you look at it as a Schrödinger picture, but as a state. So the gate you use now is a folded gate, which means it's one red brick on top of one blue brick. And the gates have the square dimension, so that's why we plot thicker wires here. So now dual unitarity now means unitality. So these circles means that just you apply either trace or you apply you glue these two indices together and you sum over. So that's why the circle. So now, so this is unitality, and if this gate is dual unitary, you get this sideways unitality. So that's nice actually, because it's not orthogonal, it's not unitary, but it's unital. So it means it applies also to stochastic gates, not only to unitary gates. I mean, that's actually a common feature which applies to both paradigms, unitary dynamics and stochastic dynamics. Okay, so now, but of course, if you have a general gate which is not dual unital or dual unitary, which is the same in this case, then of course you cannot contract it further. So this correlation function, which is for which the displacement in time and space are arbitrary, is non-vanishing. But still, I mean, you use already now the unitarity, which means I cut away everything which is outside this cone, and due to time reversal, I cut everything out which is outside this cone. So what remains is this rectangle. Now, if you want to tilt this rectangle just to make the picture nicer, then this is if you want the partition function like object, you have to evaluate in order to get correlation function. Okay, so now you see, I mean, all these empty circles are like gluing two lines, which means like putting identity operator or doing the trace, depending on which dual or forward picture you're looking at. But the non-trivial operators are these bullets, right? And these bullets are like, again, states in operator space or some operators, right? Okay, so now this is the object we're going to calculate. Now, this is a generic object, of course, and it's very hard to calculate because this is, I mean, everything scales exponentially in space and time. And so if there is no integrability or no structure, I mean, this is basically exponentially hard. We have shown later how to simplify things if these green gates become yellow gates, right? When you can contract things this way, for example, now we have tilted, but now if this green would be yellow, then we could contract this way and show that this vanishes. But since this is not yellow, we cannot do anything. But then now what we want to do in the next step is to try to do some perturbation theory where a small fraction of gates are perturbed, or where all gates are perturbed by a small parameter. So we will assume now that there is a gate which we call a perturbed gate, U eta. Eta is a perturbation parameter, which is written in this multiplicative way as a dual unitary gate times e to the I eta p, where p is some Hermitian operator of 2 qubits. Okay, so now the idea which we want to advocate now is that, suppose now first, because this is simpler, we just imagine that we take a regular sublattice of perturbed gates. This is just to show you how idea works. I mean, we can do arbitrary arrangement of perturbed gates, and we can also do density 1 of perturbed gates. But let me just, for the moment, assume that you have just a regular sublattice, then what we want to show is that this correlation function then equals a correlation function which is sum over all possible way of splitting this correlation function in paths which go from A to B and scatter on the remaining perturbed gates. So everything that goes through the yellow gates can only go through straight lines, but whenever you hit the impurity, you can scatter. It's like scattering on impurities which are perturbed gates. Now, of course, there are many ways in which you can go this way, and the point is to show under what condition the correlation function is the sum over what we call skeleton diagrams. Okay, now just to finish, I will give you one simplified context in which this can be done. And this simplified context is in a way classical context. So what we do is now make random fields which are noisy, depend on space and time. They are independent noisy fields, for example, along z direction, and then we will average over the noisy fields. We will take a correlation function, which is a two-replica object. It has two unitaries, u and u dagger, and then we will average over the random fields. Now, if you would average over the Dhar random fields, if this would be Dhar random, meaning arbitrary direction of the field, then this would trivialize the correlation function. The correlation function would be trivial and will be 0 unless x is equal to t equal to 0. Now, if you do this in this u1, so just along fixed direction, u1 average noise, then this is not trivializing dynamics, but it makes dynamics classical, right? I mean, it basically is like, yeah, basically it replaces quantum dynamics to a classical Markov chain, with respect to diagonal basis of operators, which are the two diagonal operators, identity and sigma z. And the elementary two-qubit gate now becomes a 4x4 matrix, which operates in this operator basis of diagonal operator. So it diagonalizes any operator. So you only need to look at correlation functions of diagonal operators. Now, but this is a simplification, and again, it's a unification of quantum and stochastic. It's not really quantum anymore, if you want. But now, right, and now we can also parameterize this. I mean, this is now, it's not a stochastic matrix in this representation, is a Hadamard transformation of a stochastic matrix. So which means this matrix is parameterized by 3x3 matrix of non-positive real numbers. These real numbers will not be positive, but if you take a Hadamard, they become positive and sum to 1. So they are like stochastic matrix. Now, there are these 9 parameters, which basically parameterize this thing. And these two guys here in these two places are 0 if this is a U1 averaging of a unitary gate, of a dual unitary gate, right? And this would be called dual stochastic. This would be called a dual bistochastic. I mean, these gates are bistochastic by definition. Unitarity corresponds to bistochastic because they are stochastic and reversible, if you want. But now, if you have this epsilon equal to 0, this corresponds to dual bistochastic. Sorry. And there is a nice kind of tiling representation of these correlation functions. So for example, now there is a single non-trivial operator, which is sigma z. So I don't put A and B here anymore. I just put bullet. Bullet means sigma z here, sigma z there, and I write correlation functions. And now correlation functions are these sums now, and this S now is just 0 or 1, which is identity or sigma z. There are two states in this operator space. And now this correlation function now I can write as a sum of all diagrams, which are all possible tilings of this rectangle in a way that there are no dangling ends. So basically you can assign a tile to each of these non-vanishing weights, one being anti-tile, and then all these guys having these assignments. And the ones which actually correspond to non-dual bistochastic are these epsilons that correspond to terms. So which means that whenever you have a term, I mean, which means that if you have dual unitary or dual bistochastic gate, then you should have no terms. Which means these correlation functions will be non-zero only when you go straight here or when you go straight there. So these are the two light rays, which means that we showed before that the correlations can be non-vanishing only along presentation that there should be no terms. So then now the perturbation theory works like that. I mean, you just count number of terms, and this gives you the order in perturbation theory. So for example, the second order in perturbation theory, for example, the leading diagram would be this one, which would also have no loops. But then there would be other diagrams in second order which would have loops. And now the point is, and this is basically the last point I want to make, but it's the crucial one. The point is now to show under what condition the loop diagrams don't contribute. And that can be written in terms of a theorem if you want. Namely, there is a simple set of conditions to check. Namely, these are the parameters of the gate, A, B, C, D, E, F. These A, B, C, D, E, F are the parameters of the gate. And now there is a condition to check if these guys, these two conditions are met, where these alpha and beta are the singular values, larger singular values of these 2x2 matrices. Namely, if these two conditions are met, then the dial sum can be explicitly evaluated and shown to be equal to the sum of skeleton diagrams. So that means the convergence of the perturbation theory can be proven in the low density regime. I mean, that is the rigorous part of the low density regime. So if you assume that the density of perturbed gates goes to 0, but it turns out, I mean, we show a lot of numerics to back up the conjecture that it works actually for any density of perturbed gates. Okay, I think that maybe was a bit quick, but I'm happy to go into more depth in case there is questions. So let me just go to the conclusions. So basically the main points I want to stress is 3 points. So first, that these ideas of dual unitary many-body dynamics can allow us to provide first exact results on spectral statistics of extended quantum lattice systems, when thermodynamic limit is taken first. We can also write even simpler exact results on spatial temporal correlation functions, and we can classify dynamics to be regular, ergodic, and mixing. And third is that we have strong indications that these results are structurally stable to perturbations. There are many interesting directions which I would like to follow next, but there are still obstacles. For example, I mean, one of the most pressing one is if there is some possibility to find some exact results for finite systems, finite size corrections. I mean, it turns out that all these results are very crucially depending on the fact that I do thermodynamic limit first. If I don't want to do that, then I need different ideas. And in particular, why I'm kind of excited about this possibility is that dual unitary circuits, in principle, maybe not promise, but they look promising to be models where one can prove ETH. But again, I mean, there is this obstacle there. But we have some numerics. I mean, there was a paper we had, I don't cite it here, but there's a paper we had a couple of months ago with Felix Fritsch in our group, where we provide some numerics and some heuristic ideas how this should work. And then something which is obvious, but yeah, I didn't discuss much yet, is to extend these concepts of dual unitarity to driven dissipative quantum chaotic systems by extending this to, let's say, to dual bistochastic Krauss circuits. I mean, one can also define Krauss circuits which become regular Krauss circuits in space and time direction, and this should then be again exactly solved using the same tricks. So with this, I would like to thank for your attention and finish.
Thank you very much, Thomas. Very nice talk and many interesting topics. So now the session is open for questions. People who have a question, raise your hand and I call your name. So I have several questions, and can I ask while the people are thinking? And you showed the CUE universality and the first topic.
Which one? COE.
CUE. Yeah. And you put disorder. What is you don't see the many body localization in this system.
No.
So what happens if you consider non-dual gate?
No. Yes. Okay. So that's actually the question, the slide which I skipped, but I can now put it on. So, for example, I have a couple of. I mean, this is unpublished. This slide is unpublished calculation. So this is basically But this is what happens when you take a non-dual unitary gate. So now this gate is, let's say, generic gate, which has some distance from nearest dual unitary gate, and that distance from nearest dual unitary gate, I think, is increasing is decreasing in this direction. So this is more dual unitary, this is less dual unitary. And this is spectral form factor minus t to power 1 over L. And you see that is in this particular kind of units, this curves seems to show some sort of scaling behavior when you increase the system size. So this is different system size, 8 to 10, 12, or 10, I don't know, from 8 to 16. Yeah, from 8 to 16. And the last two are basically already overlapping. So, I mean, so now, I mean, what I want to say is, of course, I cannot show anything. It becomes very hard, but there might be some bounds. And one can conjecture bound like this in red. Now, it's very hard to provide any substance to this bound. But if suppose that one can prove, and this bound is just inspired by numerics, but suppose this one can prove this bound, then in principle, one could show that basically, yeah, I think this bound would show that there could be no Mani-Wada localization. Because it would show that basically for long times, there is always exponential convergence to random matrix, which does not depend on system size. Well, it depends on system size, but very weakly. So, I mean, there is this, and then there is, I want to mention, there is this paper by Sam Garrett and John Chopper, who defined this, who defined these eigenvalues of the dual transfer matrix, and they call them spectral Lyapunov exponents. And then, of course, one can, and then they have another paper, PRL, I think slightly after this, where they say that the many-body localization transition could be related to spontaneous symmetry breaking. Now, of course, if you invoke this scenario of spontaneous symmetry breaking, then what I'm saying might have a crossing. I mean, might not be true, or there could be still a critical value of disorder where this breaks down, where symmetry breaks somehow, and but yeah, I mean, it's just I mean, maybe you have seen them, and we had put out a couple of papers, so 1 or 2 papers where we have questioned the existence of many-body localization based on numerical analysis of spectral form factor, for example. And now, of course, this has produced a lot of debate. And again, I mean, the results look very simple, right? So now, my kind of understanding is that the resolution that there is no many-body localization transition in thermodynamic limit is the simplest explanation of the data. It's not the only explanation, but it's the simplest. So usually the kind of principle of Occam razor is kind of the natural principle in science. But of course, we don't have any idea how to prove that. So, but the original question was, of course, about no, I'm not. No, I'm sorry. That's it.
No. Yeah, thank you very much. So they don't say about the critical value for the transition.
No, you mean this Garrett paper?
Yes.
No.
Okay, so we have another people who have a question. Jacopo, please.
Hi, Tomas.
Hi, Jacopo.
Yeah, so, but this in this perturbative scheme, so at least in the low density, I mean, can you see this as a, I mean, is the space of trajectory doing some random walk? I mean, can you see some spreading correlations increasing, I don't know, as a square root of t or something like this? Around the light cone, let's say.
Yeah, that's a good question. It's hard to say, of course. I mean, you see, I mean, it's very hard maybe to do. Well, I mean, yeah, I mean, maybe we just didn't analyze them in the way that you are interested, but. For example, there is a couple of figures we have in the PRX where we show how you spread your I mean, how the correlations spread inside the light cone. It doesn't look very, I mean, it's like still you had this main contribution, which is from the dual unitary part, which is this two light rays, the main delta function. And on top of that, there is some smooth, exponentially small background. Now, of course, you are kind of, I mean, you think about in terms of, hydrodynamics, right? I mean, you would like to have correlation functions of conserved charge, conserved densities, right? Yeah, imagine, I mean, this is not yet related to anything conserved. So now, I mean, these objects have no conserved charges, right? I mean, these are the simplest circuits where there is no conserved charges. Now, the next level would be to build this, I mean, to build conserved charges in. I mean, it's possible, but it's not, I mean, we have not yet looked into any of those.
But okay, but anyway, but you say that this is shows some structural stability, which is not true for integrable models. But for example, don't you think that you would have a similar behavior if you take rule 54 and you add impurities a bit the same way you're doing? Like you would have wouldn't you have like similar like trajectories for the solitons?
Yeah. No, and yeah, for the rule 54, I don't know how to, well, I mean, in case I want to preserve its cellular automaton character, I cannot smoothly deform it, right? I cannot perturb it smoothly. Of course, I can perturb it to make it a quantum or stochastic model. No, but yeah, I'm not sure.
Okay, it's just an intuition that you think that the same procedure cannot be done for integrable case.
Well, I mean, yes. I mean, to be honest, yeah, it might be it might be misleading what I said, because what you do for, I mean, what you can show, one thing is the stability of trajectories, and the other thing is stability in terms of correlation functions or statistical solutions, let's say statistical states in a sense. And that can be two different things, and these are more stable than trajectories, of course. So it could be that could be made stable even for integrable systems. But again, then there is this issue that we discussed, this KPZ related to integrability. That certainly is, well, again, we can discuss, but I think it's certainly unstable with respect to perturbations. Yeah. And that is something which is structurally unstable, really, right? It becomes different in resulting class. I mean, when you break integrability.
Okay, thanks.
Are there any other questions? Benjamin Doyon.
Yeah, hi, sorry. No, I had raised my hand, but I think it was the same question as Jacopo, basically. If you can relate your result to hydrodynamic kind of a form of correlation functions, or eventually prove some part of hydrodynamics.
Yeah. Yeah. I mean, yeah. I mean, I cannot give you really any more coherent answer than I did to Jacopo. Yeah. So.
But so just to come back, so you say, I mean, so there should be some conserved charges in there, right, to somehow explain the correlation functions. Do you think there are no conserved charge at all, so it is not related to this concept?
Well, you mean where? Which conserved charges where?
Well, somehow from the dynamics, right? There should be a notion of conserved charges there. And
yeah, no, I mean, actually, yeah. So we actually discussed these conserved charges also in various contexts, like in this. I mean, in one post paper with Bruno and Paolo. I mean, we have classified dual unitary circuits which have conserved charges, right? But they are not. I think they are not so interesting with respect to transport. I mean, they are. I think this has two trivial properties. I mean, they are just ballistic. So
yeah.
So I don't know. I mean, I think we didn't really seriously start thinking about this yet. So, but it's something. I mean, I would say that one needs probably to go beyond qubits to get something more interesting.
It's just that the intuition. Sorry, my intuition would be that if you have strong correlation on the light cone somewhere, so that somehow something should transport these correlations, and that thing should correspond to some kind of conserved charge of some sort, maybe not the trivial one, not the kind of intuitive one you can think of, but in some kind of general formulation. Otherwise, you would expect everything to decay.
No, but yeah, but you see, I mean, in this kind of simple picture of this correlations in dual unitary circuits, I mean, everything decays exponentially. I mean, so
Yeah.
I mean, everything is given in terms of a 1 qubit, 0-dimensional quantum channel, yeah, which has a finite spectrum. So there is no way for power law decay of correlations.
Right. Yes.
So one needs to do something. I mean, yeah, maybe just this framework just doesn't allow for something.
Right. You understand.
As we need, but yeah.
Yeah, thanks.
So the last question, Barbara Chandani, please.
Hi, so at some point you mentioned KAM stability. I was wondering, within the dual unitary models themselves, you can get both regular and chaotic behavior, can't you? And is there a way to get an interesting transition between the two of them, or is the KAM theory in a way simplified because you just have these continuous tuning parameters?
So you're asking about these models or KM? I mean, the classical KM, or
no, sorry. Within the dual class of dual unitary models, you have both ergodic and non-ergodic ones, right?
Within which class?
That you described at the beginning of your talk.
Yeah. Okay. These dual unitaries. Yeah. Okay.
Yeah, and I was wondering, is there an interesting KAM transition between those two, or it's really just you change a few tuning parameters?
Well, you just tune the parameters. I mean, this is much less rich because everything is finite. It's finite dimensional dynamics, right? It's a 0D. I mean, geometrically 0-dimensional because it's just dynamics along the light ray. And there you just tune parameters and you go from, for example, you can take a case which you have where you have a eigenvalue on a unit circle, which means you have conserved charge, and then you tune parameter and you can start to decay. I mean, you can engineer transitions, but these are not very deep because they are in special context. I mean, that's why I'm kind of excited about, really going deeper into this perturbation stability, because if you can find such phenomena which are perturbatively stable, then it's much more exciting.
Okay. Thank you.
Okay, so time is up. So Thomas, thank you very much for a very nice talk. And let's thank the speaker